Hello Math 1224, this is Dr. P with Lesson Launch 13.1, a winning formula. So the first thing I want to do in this video is make a distinction between two concepts that you've now heard of. One of them is the concept of a function, and a function might be, for example, something like this. It might be something that we call f, and then it has a domain, which is the real numbers, and then it might have some codomain, which is the real numbers. Now let me explain what that terminology means. Some of it you've heard before. So when I write this notation here, this refers to the name of the function. That name of the function in this case is f. This tells me the domain of the function. That's the set of all possible inputs. And then this here tells me something called the codomain of the function. That's the set of all possible outputs. Possible outputs. There we go. Okay. I say possible outputs because there's another word called range that you may have heard of before. When I use the word range, I mean the set of all outputs actually attained by the function. Not a distinction we need to worry about too much right now. It's just that's why there's this separate word called codomain. Okay, anyway, what is a sequence? Well, a sequence is also a function, but it's a function with usually a different domain. So a sequence might have a name like A, and it might have domain, something like the natural numbers, or it could be the natural numbers plus 0 or something. And for this course, the codomain is still going to be the real numbers. So it's a function that maps every natural number, for example, to a real number. And the way that we write the formula is a little bit different. If we were using function notation, we might say something like a sub n equals n over n plus 1. And that's a perfectly fine way to write a function formula, and in fact it's a perfectly okay way to write a sequence formula. But just for reasons of having a different notation for sequences, we usually use this notation instead. A sub n, subscript n, equals n over n plus 1. And that is called an explicit definition for a sequence. That's an explicit definition for a sequence. It's explicit not because it has like adult content or anything, but because it tells us exactly what a sub n is in terms of the input, directly in terms of the input. And we're going to give an example of a different way of defining a sequence later on. But first I want to do a few things with this definition. So one of the things is we could make a table of values, just like we would make a table of values for some other kind of function. But we could create a table of values by listing out some possible inputs. Listing out some possible inputs n, and their corresponding outputs a sub n. So for example, we might list out the first 4 or so terms of the sequence. So if n is 1, then we would get a sub 1 equals 1 over 1 plus 1, which is 1/2. If n is 2, then a sub 2 is equal to 2 over 2 plus 1, which is 2/3. And then a sub 3, we could use the formula again and get 3/4. And then a sub 4 would be 4/5, and so on. The nice thing about a sequence is I can actually say what the first few values of a sequence are. I can't say what the first few values of a function are usually because there's no such thing as the first few real numbers, the first few positive real numbers, but there is such a thing as the first few positive integers, and that's usually a nice way of getting started understanding a sequence. Anyway, that's a numerical way of understanding a sequence. There's also a graphical way of understanding a sequence, and that is using an actual honest-to-goodness graph. So to do that, I could draw a set of coordinate axes in the usual way, devote the horizontal axis to the input, n, and the vertical axis to the output, a sub n. Remember, a sub n represents the output of this function. And just looking at this, it looks like all of my function values appear to be between 0 and 1. So I'm just going to set the scale like this. I'm going to set 1 here. And then the n-axis, I'm going to put 1, 2, 3, 4 here. And then I can create a graph just by plotting several ordered pairs, where each ordered pair has an input on the horizontal axis and an output on the vertical axis. So when n is 1, I got a sub n equals 1/2. A sub 2 is equal to 2/3. A sub 3 was equal to 3/4, a sub 4, 4/5, and so on. Now, you might be tempted to connect these dots and get some kind of curve. My dot connecting skills on this tablet still not very good. Now, that's what we would do perhaps if we were trying to graph a function whose domain is the real numbers. But here, the domain is just the integers. In fact, it's just the positive integers. So there's no curve, there's no actual curve connecting those. You might draw some kind of trend line just to give yourself a better idea of what the function is doing, what the sequence is doing. But that's optional, and there's nothing about those points in between the points that I marked here that is official. There's nothing there that's officially part of the function, just these 4 dots so far. Okay, anyway, so that's a way of graphing a sequence, is just think of it as inputs and outputs and plot those in the coordinate plane. All right, so anyway, that's an explicit definition for a sequence. I promised you there would be a different kind. Here's the different kind. Let's see, I'm going to just go ahead and zoom in again so things come out roughly the same size. There we go. So that was explicit. Now, what's the opposite of explicit? It's actually, in this context, it's not implicit. It's something that we call a recursive definition. I guess you could call it implicit. I don't know. I hadn't thought about that before. So this is an example of a recursive definition. Let me just bring this over and make this the focus here. Okay. So suppose I give you this information. I'm going to give you 2 bits of information about a sequence. So I'm thinking of a sequence. It's different from the last one. I'm going to say b0 is equal to 0. So this is going to be a sequence that begins with a 0th term. And for all n, I'm going to write b sub n plus 1 equals b sub n plus 1 all over 2. And that's true for all n greater than or equal to 0. So what this is saying is I can pick any non-negative integer here. I can look at that term of the sequence. So the 3rd term of the sequence, for example, n equals 3. Add 1 to that, divide by 2, and I get the 3 plus 1, that's the 4th term of the sequence. So this is a way of defining a sequence that defines each term of the sequence in terms of the previous term. That's why it's called recursive, is if I want to find the 100th term of the sequence, well, then I got to think about the 99th term of the sequence, and then, well, what's the 99th term of the sequence? Then I put that in here, and then that forces me to think about the 98th term and so on. It's a recursive process. And not a particularly fun one, actually. It's not much fun to do. But sometimes we get lucky. Sometimes we are able to come up with an explicit definition using the recursive definition, just by using algebra and our detective skills. And that's what I want to try to do here. That sounds like a fun little adventure. Maybe you don't agree, but that's what the rest of this video is. So let's see if we can do it. So let's investigate this. Investigate. All right, so we're going to investigate this numerically using a table of values. So I'm going to create a table of values, n, and then b sub n. And then think about what the first few terms of the sequence would be. Well, first of all, we already know the 0th term. b0 was defined to be 0. By the way, you might be wondering why I put that there. Like, why do I need 2 pieces of information for this definition? I should say a bit about that. If all I give you is this, then what's the first term of the sequence? We really have no way of knowing, because if all I have is this, then all I have is a way of determining one term of the sequence from some other term. If I don't have any of the terms, then how do I even get started? That's why I need some starting point here. So here I got b0 equals 0. Anyway, if n is 1, then I'm going to use this information over here, and I'm going to be using this like crazy, so I'm going to put a box around it there. That's going to be the most useful thing from now on. b sub 1 is equal to, according to that formula, it's equal to b sub 0, because n is 0 in this instance, plus 1 over 2. That's 0 plus 1 over 2, which is 1/2. Okay, that's nice. That's not such a bad number, 1/2. All right, let's see what happens if n is 2. If n is 2, then b sub 2 is, let's see, that's going to be b sub 1 plus 1 over 2, which is, well, b sub 1 was 1/2. So that's 1/2 plus 1 over 2. I believe that's 3/2 over 2. I think that's going to come out to 3/4. Okay, that's cool. That's interesting. So now I've got fourths. I don't know, this might get worse. We'll see. If n is 3, then b sub 3 is going to be, what? Let's see. According to that recursive definition up there, let me just show that one more time. All right, see that? Just zoom out a bit so we can see all that at once. There we go. going to be b sub 2 plus 1 over 2. Well, b sub 2 was 3/4. That's what we just figured out. So 3/4 plus 1 over 2, that comes out to 7/8. Okay, so I've got the first two terms of my sequence are 0, 1/2, 3/4, 7/8. And I'm wondering at this point if you see any kind of pattern here. It might help if I rewrote this 0 in a different way. That can be thought of also as 0 over 1. You might notice that the denominator always seems to be a power of 2, and that power of 2 is growing very predictably. It kind of looks like the denominator of b sub n in each case is 2 to the n. Like, that seems consistent with what we have so far, right? Because b sub 3 had a 8 in the denominator, and b sub 2 had a 4 in the denominator. I think if I found b sub 4, that would probably have a 16 in the denominator. In fact, it'd be 15/16. So that denominator seems to always be 2 to the n. The numerator, harder to find a formula for it, but I do notice that it seems to be connected to the denominator somehow. It seems like the numerator is always 1 less than the denominator. Well, denominator is 2 to the n. That would make the numerator 2 to the n minus 1. And then you might think, oh, there's a nicer way to write that. 2 to the n minus 1 over 2 to the n. I could split that up. And then that first term there is just 1 minus 1 over 2 to the n. And if I look at these terms here, that seems to agree with what I have here. If n is 0, then this is 1 minus 1 over 1, that is 0. If n is 1, then I get b sub 1 equals 1 minus 1 over 2, that's 1/2. That agrees with what I have here. And in fact, this formula will agree with each of these terms. Now, that does not prove that this is a formula for b sub n. To do that, I would need to do a little bit more work. And I'll just say what that work is here. It's not going to be a major focus of what we're doing. I do want you to be able to generalize a pattern and find a formula, but being able to prove it is something that we would probably focus on more in a subsequent course, like Foundations of Math. But I do want you to see that this seems to be a good generalization of what's going on here. If you wanted to prove it, by the way to prove it would be go back to this definition here. Check that what we have here agrees with b sub 0 being 0, which we already did check. And then to verify that this formula is consistent with this recurrence relation. That, by the way, is called let me write that down. It's called a recurrence relation, because it relates one term of the sequence to the previous term. Anyway, you could actually go through and substitute what this would be if the input were n plus 1. Substitute that in here, and then substitute b sub n, that is 1 minus 1 over 2 to the n here, and verify that this relationship works out. If this formula here is consistent with both the initial term and the recurrence relation, then that actually proves by mathematical induction that this is the formula for the sequence. And by the way, this is an explicit formula, which is usually nicer to have. It's usually more useful to have an explicit formula or explicit definition than a recursive one. But sometimes a recursive one is all you get. And sometimes it's very hard to solve that recursive function or that recursive definition to get an explicit one. This was a very special case here where it wasn't so hard. Anyway, so that video contained a little bit of everything. It contained a little bit about different formulas for sequences, explicit and recursive, and even a little bit about how we might untangle a recursive definition to get an explicit one. But again, it is pretty rare in the grand scheme of things that that's possible. I really mostly use this as an example of how we think through looking at some terms of a sequence to come up with a general formula, because that's something that we'll need throughout the rest of the course. Anyway, that's all the lesson launch we're going to do here. I will see you in class.